Boys and girls, this will be the last video of this semester. In chapter 21.4, we're gonna talk about the relationship between the free energy of the electrochemical system and the equilibrium constant and the electrical work. So in chapter 20, we talk about the relationship between the free energy and the equilibrium constant of a chemical reaction. So in this chapter, we're going to specifically talk about that relationship happen in the electrochemical cell. The sign for delta G and the cell potential are opposite for a spontaneous reaction. Right? So for delta G, we want it to be negative, but for E cell or the cell potential, we want it to be positive, right, for a spontaneous process. So actually, we can relate the free energy with the cell potential using this equation. Right? So this delta G equal to negative NF times cell potential. Right? So at standard state, we will add this standard notation for the free energy and the cell potential. But at some condition other than the standard state, right, without this standard condition, right, this equation still applies to the to this delta G and the E cell, right? So in this case, we don't have the standard notation, right? Yeah, right. Oh my, so hard to write here, right? So whether a standard condition or not, right? This equation applies. So here in this equation, we have N is actually the number of moles of electron being transferred, right, in this redox reaction. Right? For example, zinc can replace copper. That's 2 electrons being transferred. Right? For each mole of zinc reacted, there will be 2 moles of electrons being transferred. Right? So that's the number of electrons transferred in moles. And the F is a constant, Faraday constant, right? So equal to this certain number. So notice the units, right? So we can apply it in the equation and cancel out the unit, right, to achieve the correct unit for delta G. So in chapter 20, we learned that delta G is actually equal to negative RT times natural log of equilibrium constant. Right here, T is the temperature in Kelvin, R is the universal constant, right, 8.314, right? So because we have delta G on both sides, right? So that means this negative NF E cell is equal to negative RT natural log of K, right? So we can establish this equation here, right? So what we can do here is we can divide negative NF on both sides, right? So we can divide negative NF on both sides. So we ended up with this equation. So the standard cell potential, right, will equal to RT divided by NF times natural log of K. Right, so we can further, right, simplify this equation, right, if we consider the standard condition, right, because here the E cell is the standard cell potential. So at standard condition, this T is a room temperature, right? R is a constant, F is a constant, right? So this equation can be further simplified, right? So by substitute those constant into the equation, and then also we turn natural log into log, right? So natural log is E based, and this log is 10 based. So eventually we get this equation, right? So the standard half cell potential is equal to 0.0592 volt divided by the number of moles of electrons being transferred times log of equilibrium constant, right? So we have a clear relationship between this standard cell potential and the equilibrium constant. Right, so now we can get this triangle, right, diagram showing the relationship between free energy, standard half cell potential, and the equilibrium constant, right? This is standard free energy, right? So the relationship is written here above the arrow. So when delta G is for spontaneous reaction, right? So we want delta G less than 0, and this E cell greater than 0, and in this case, this K, right? This K must be greater than 1, right? So if K is greater than 1, right, the log K, right, will be greater than 0, right? So if K is equal to, right, so K is greater than 1, right? So this log K will be greater than 0, right? If K is less than 1, this log K will be, right, less than 0. Right, so if K is equal to 1, log K will be equal to 0. Right? So remember these relationships. Okay. Right, so at equilibrium we have delta G equal to 0, E equal to 0, and that's when K is also equal to 1. Right? So for electrochemical process, right? So the equilibrium constant will be equal to 1. That's when you have the same concentration of the two electrolyte solution. Right? When you we can talk about more about that later in this video. Let's work on an example problem, right? Calculating the equilibrium constant and the standard delta G from the standard cell potential, right? So we have this equation, elemental lead replacing silver, right? So generating this elemental silver, right? Silver is a more valuable metal. So we want to calculate K and the delta G at room temperature. So from Appendix D, right? Remember our group friend, right? Last chapter 20, we look at Appendix B, right? So for this chapter, we'll use Appendix D, right? So you can find this standard, right, half cell potential for each half reaction, right? So after we, because here silver cation is being reduced to silver metal, right? So we still keep it in the reduction form, right? So that this number will go to the front here, and then we reverse the reduction of lead, right? So that's minus, right? So negative 0.1 negative 0.13. So the standard cell potential is positive 0.93, right? So if we know this value here, and then remember this relationship between delta G, right? This E and the K, right? E cell and the K, right? So if we know any one of them, right, we can get this the other two, right, using these relationships. So if we know the standard cell potential, right, we can apply this equation to calculate equilibrium constant, right? So again, this is a simplified version of this equation when it is at room temperature, right? That's when T is equal to 298 Kelvin, right? So it only look equal to this number, right, when K is equal to 298, right? So the other temperature is no longer standard condition, right? So you can no longer use this equation. So we got, because the number of electrons being transferred are 2, right? So in each half reaction, right? So this number of electrons being transferred. So the denominator n here we have a 2, right? So we have this equation here equal to the half cell potential. So we can calculate K, right? So K is equal to 10 to the negative 31. So it's a very large number, right? Meaning that this reaction is very favorable, right? It's spontaneous. So then using this E cell, we can also calculate delta G, right? So that's equal to negative NF times this E cell value, right? So plug in those constants, right? Again, n here is equal to 2, and we can calculate this delta G, which is a negative number, right? So meaning that it is spontaneous. So far, we have considered the cells at standard state only, right? So at standard conditions. But most cells don't start with those concentrations, right? With 1 molar, 1 atm, right? Pure solid, right? So most cells do not start with those conditions. And even if they did, the concentration changes as the cell operates, right? So in our batteries, actually, the reactant concentration are very far away from those standard state condition. So to determine the actual cell potential under non-standard conditions, right? That means this E cell, right, are without this standard notation, right? So if we want to calculate this non-standard state cell potential, right, we need to derive an expression for the relationship between this E cell and the concentration of the reactants in the electrochemical cell based on the relationship between delta G and the concentration, right? So in chapter 20, so when we try to calculate the free energy, right, not the standard free energy, right? So when we want to calculate the free energy, it's actually equal to the standard free energy, right, plus RT times natural log of the reaction quotient, right? So in this case, the concentrations of the reactants are no longer at standard state, right? So we can derive this equation, right? So how about we can use this equation, right, to relate that into the cell potential in electrochemical cell, right? Because from the previous slide, right, we know delta G is equal to this, equal to negative NF times E cell, right? So the standard delta G is equal to negative NF standard E cell, right? So we keep the RT natural log of Q, right? So again, if we divide a negative NF on both sides, right? If we divide negative NF on both sides, on the left hand side you have E cell, right? This is the cell potential, right, at non-standard state, which is equal to standard cell potential minus RT divided by NF times natural log of Q, right? So you see the format is very similar, right? So for free energy, the free energy is equal to standard free energy plus RT natural log Q, right? But for cell potential is equal to standard cell potential minus RT divided by NF times natural log of Q. Right, so if we again, right, plug in those constants and assume temperature is equal to 298 K, right? So that this equation can be further simplified into this form, right? That's true when temperature is at room temperature. So again, n is the number of moles electron being transferred. So based on this equation, right? So when Q is less than 1, when Q is less than 1, that means log Q, right, is negative, right? So log Q is less than 0, so it's a negative. So your natural log Q less than 0, right? So your log Q is also less than 0, right? So the E cell will be greater than the standard E cell, right? So the actual cell potential is greater than the standard cell potential, right? So when this Q is greater than 1, right, that means natural log Q and the log Q is also greater than 0, so that makes this term positive. So your E cell here is less than the standard E cell. And when this Q are equal to 1, remember when Q equal to 1, that means at standard condition, right? At standard condition, everything, the activity is equal to 1, right? 1 molar, 1 atm, those things, you know. And so the E cell is equal to the standard E cell, right? So that's at standard state. So now let's use this example problem to demonstrate how we can use the equation we developed in the previous slide to calculate the cell potential at non-standard state, right? That equation we developed is also called a Nernst equation, right? So here we have an electrochemical cell with zinc and hydrogen electrodes, and it's no longer at standard condition, right? Because zinc 2 plus is at 0.01 molar, and the proton, right, is 2.5, and the pressure is 0.3. So none of them is at standard state. So we want to calculate the cell potential at room temperature, right? So in this case, right, so again using this appendix D, right, so we can figure out which one is the cathode, which one is anode by looking at their position, right? Looking at the position of their reduction half reaction in the list, right? So zinc, right? Zinc is more reactive than hydrogen, right? So zinc is below hydrogen proton reduced to a hydrogen gas, right? So zinc is being oxidized and the proton is being reduced, right? So we keep the same half equation for proton being reduced to hydrogen, right? So this is equal to 0, right? So that's from the appendix. And this is for first we calculate the standard, right? Standard E cell, right? So first let's find the standard E cell, right? So for the zinc, right, we reverse it, right? So we have 0, right, which is high pens at the reduction, minus the potential at the oxidation at the anode, which is negative 0.76. So overall, we have a 0.76, right? Notice that is the standard cell potential, right? So because we need that, right? We need that to calculate the cell potential. So now we get the standard cell potential, right? So we need this Q value, right? So in terms of the Q value, right? Because we can look at this overall reaction, right? So this overall reaction Q is equal to, so hydrogen is in the gas form, so we use its pressure in atm, which is given, right? So zinc, right? Zinc is aqueous phase, right? So we use its concentration, and for proton is also aqueous phase, so we use its concentration. But remember the 2, right? So we have to do the proton concentration square. So all this concentration or pressure are given, so we can plug in those values, calculate this Q value, right? So we can substitute this Q value into this equation. So we know the standard E cell potential, we know the Q value, right? So this V is unit, right? This V is unit in a volt, right? So here N, right, we look at the half reactions, right? There's 2 electrons, right? So N equal to 2. So everything is known, we can calculate this E cell, right, is equal to 0.86, right, which is actually, right, greater, right, it's greater than the standard E cell. So we all know that when an electrochemical cell operates, right, the concentration, right, in the electrolyte, it changes, right? So when zinc replaces copper, right, zinc 2 plus, the amount of zinc 2 plus is increasing and the amount of copper 2 plus decreasing, right? So when this concentration changes over time, right, so how do we predict or how do we calculate the cell potential, or as this concentration changes? Because as with any voltaic cell, right, the potential, right, so of the zinc copper cell changes during the cell operation, right, because its concentration of zinc and the copper changes, right? So Q changes, right? So Q also changes as this cell operates. So let's say, for example, when this zinc, right, is equal to this concentration, and copper is equal to this concentration. So what is the cell potential? Right, so this could be at any moment, right? So with this concentration, we can calculate Q, right? Because if you look at this overall reaction, right, we have 2 solids, and solid doesn't appear in the expression for Q, right? So we're only looking at the concentration of zinc 2 plus and the concentration of copper 2 plus, right, which is equal to this. So when their concentration are given, we can plug those in, right? So here N equal to 2, right? N equal to 2, right? So the standard cell potential we can get from the appendix D equal to 1.1. So overall, with this concentration of zinc and copper, the cell potential is 1.23. Right, so we can do this for any combination of zinc and copper concentrations, and then we can plot this relationship between the cell potential, right? This is the non-standard cell potential, right, versus this Q. Q is actually the ratio, right, of zinc concentration over copper concentration. Right, so we know that when they're equal, right, when they're equal, Q equal to 1, this is at standard state, right? So the cell potential is equal to standard cell potential, right? So, but when this Q is less than 1, right, the cell potential is greater than the standard cell potential, right? It's greater than 1.1. And when this Q is greater than 1, the cell potential is less than 1.1. So in the previous slides, we see that if we have a different, right, concentration of the reactants, right, the cell potential can also be different, right? So that's due to this different concentration. But what if we have the same type of cell, right? So what if we have the same type of cell, meaning that same electrolyte, same type of a solution, but with different concentration? Is there gonna be a potential, or is there gonna be a difference in terms of their electrical potential between the two electrodes? And the answer is yes, right? Just think about when you mix a concentrated solution with a diluted solution, what's gonna happen, right? So for example, if you have a beaker with 1 molar sodium hydroxide and another beaker with 0.1 molar of sodium hydroxide, what if you mix the two solutions together, right? The concentration is going to be somewhere in the middle, right? So same thing with this electrochemical cell with the same electrolyte solution but different concentration, right? So in this figure, say you have two half cells, right? They all have copper as the electrode, but one of the electrolyte solution is 0.1 molar of copper, the other one is 1 molar of copper, right? So because right now this everything is connected, right? So it's not balanced, right? The system does not prefer to stay this way because here you have lower concentration and on this side you have a higher concentration, right? So due to this sub-bridge, right, connecting these two electrolyte solution, it doesn't want to stay at this concentration. It want to neutralize each other, or like some kind of diffusion is gonna happen, right? This copper actually, right? So they want to have the same concentration in both beakers. So what's gonna happen is that for this beaker on the left, right, the concentration is so low, so the copper solid here, this electrode, it will generate more copper ion, right, to increase this copper concentration. But on the other end, this copper here, right, so because this concentration is so high, you want to decrease. So some of this copper too, right, will become copper solid and will be deposited on this electrode. So over time, right, so they reach this equilibrium concentration, right, which is basically the average of these two concentrations, 0.55. So because this copper solid on the left is being consumed, right, you can see it's being consumed, and this on this end more copper is deposited on the electrode, right? You see more copper. So right now, when their concentrations are the same, right, there's no longer reaction happening, right? So the voltage is equal to 0. But when the concentrations are different, as the picture on the left shown, you actually can detect a voltage here, right? So meaning that when you have the same electrode but different electrolyte concentration, right, you can actually generate a spontaneous cell or voltaic cell, and that type of cell is called concentration cells, right? So that means this type of cell is truly based on the different concentration of the reactants, right? So for this type of concentration cells, right, because the electrode is the same, right? So this standard E cell, right, is still equal to 0. Right, this standard E cell is still equal to 0, right? Because you're using the same equation in the appendix D, right? So no matter what you do, they're equal, right? So the E cell, standard E cell is equal to 0. But this non-standard E cell is no longer equal to 0, right? It is not equal to 0. And the magnitude will depend on the ratio of the concentrations. Right, so in this case, right, let's again look at this two figures here. Right, so this picture on the left is the initial condition, and the picture on the right will be the final condition. Right, so you basically you have a oxidation, right? So copper generating more copper ion, right, which is what's happening in the beaker on the left. And on the reduction side, you have more copper ion, right, becoming copper solid, which happens on the beaker on the right. So you can add these two together, right? So because they have the same potential, standard cell half cell potential, so this E cell here, right, so is equal to 0. And then by adding them up and cancel out the common terms, right, the copper solids, the electrons, what you ended up is, as the overall reaction is higher concentration of copper go to lower concentration of copper. So that's actually the overall cell reaction. It looks really weird, right? So how can one thing become the same thing with lower concentration, right? So this is actually not a chemical reaction. It's actually, right, this kind of like having the same concentration, right, in both beakers, right? That's like a neutralization process or averaging process, right? So the concentration, a higher concentration become lower, and the lower concentration become higher. So for this process, right? So in terms of calculating this cell potential in this concentration cell, right? So we said the standard E cell is still equal to 0, but the rest of this equation, right? So we can still apply this equation at room temperature. So we have diluted concentration divided by concentrated concentration, right? So we can make the calculation, and that's the potential, right? So which is, right, what we measured here, right? So again, let's emphasize the feature of this concentration cell, right? So yeah, this is purely based on the different concentration of the electrolytes, right? So you have the same electrode, same electrolyte solution, but with different concentration. So the standard E cell is still equal to 0, right? So this is still equal to 0, but the concentrations are not equal. So Q is not equal to 1. So this E cell is not equal to 0. Right? So based on the ratio of these different concentrations, right, we can plug that into the equation and calculate the cell voltage, potential for this concentration cell. Right, so let's work on an example, right, for this concentration cell. So we have this voltaic cell again, right? So meaning that this should be spontaneous, right? So we have two silver electrodes, both immersed into this silver plus electrolyte solution, right? So one of them has a 0.1 molar, the other one has 4 times -4 molar. So it asks us what's the cell potential at room temperature, right? So basically you're trying to get from high concentration to a low concentration, right? So when we read this overall reaction for this concentration cells, right? So on the left hand side is the higher concentration, on the right hand side is the lower concentration, right? So we apply this equation again, right? So at room temperature we can use this value here. Okay, so here the number n equal to 1, right? Because for silver, right, for silver to become a silver plus, there's only 1 electron being transferred, right? So that's why n equal to 1 here. So on the numerator we have the lower concentration, on the denominator we have the higher concentration. So for this concentration cell, the cell potential will be equal to 0.083. So there will be 3 homework problems regarding chapter 21.4, mainly on the relationship between delta G, the equilibrium constant, or the Q value here, and also the cell potential, right? So we know the relationship between each pair, right? So if I give you one of them, you should be able to calculate the other two. And also, if you know the concentration of the reactant in a electrochemical cell at non-standard state, right, you should be able to calculate the other two values, right? Calculate the cell potential or the free energy. Right, so again, this will be last video. So the remaining content in chapter 21 are more related to the real application of an electrochemical cell. So something like how battery works, or some natural phenomena related to electrochemical reactions. Right, so that's very interesting to read, because that will give you more knowledge, right, about how this electrochemical process are applied in the real world. Right, so for the final exam, we have 6 review sessions. I emailed you guys about it yesterday, and I also include the schedule, and that schedule is also on Moodle. Right, so we have a final review sessions. So there'll be 6 sessions. Each professor is gonna have 2 sessions, right? So there are 3 faculties teaching General Chem 2 this semester, right? So 2 on Sunday, 2 on Monday, and 2 on Tuesday, right? So the exact time and the link for the Zoom is in that schedule that I sent you guys, right? So you can join any of this. And from what I learned, the other 2 professors may not have enough time to cover chapter 21, or not all of the chapter 21, right? So if you have questions regarding chapter 21, you should contact me, right? So it's the best way to study the final exam, which is cumulative, right? The format is the same as the midterm 3, right? So I'm gonna make the exam available, right, early in the morning, and you can download it, work on it whole day, upload it before midnight. Right, so there's gonna be slightly more problems, right, than the midterm. Alright, so to study the content before chapter 20, just go to Moodle and go over the 3 practice exams, and also the 3 exams you have. Right, so I think I have upload the solution, right, with the exam. Right, so make sure you know everything in those 3 exams, previous exams, and make sure you do the homework, right? Make sure you do the homework in chapter 20 and 21, right? So if you have no problem with this, you'll be doing great in the final exam, and the final exam grade will replace the lowest midterm. Right? Make sure you do well in the final. Alright, so I'll see you guys in the review session.